Introduction to Intermediate Languages. In this video, we are going to see about Introduction to Intermediate Languages. Introduction to Intermediate Languages. The front end translates a source program into an intermediate representation from which the back end generates target code. Three ways of intermediate representation: syntax tree, postfix notation, tree address code. Graphical representations. Syntax tree. A syntax tree depicts the natural hierarchical structure of a source program. A DAG, that is directed acyclic graph, gives the same information but in a more compact way because common sub-expressions are identified. A syntax tree and a DAG for the assignment statement A is equal to B pointer minus C plus B pointer minus C are as follows. Postfix notation. Postfix notation is a linearized representation of a syntax tree. It is a list of the nodes of the trees in which a node appears immediately after its children. The postfix notation for the syntax tree given above is ABC minus pointer BC minus pointer plus assign. Tree address code. Tree address code is a sequence of statements of the general form x is equal to y op z, where x, y, and z are names, constants, or compiler-generated temporaries. Op stands for any operator such as a fixed or floating point arithmetic operator or a logical operator on Boolean valued data. Thus, a source language expression like x plus y pointer z might be translated into a sequence. T1 is equal to y pointer z. T2 is equal to x plus T1, where T1 and T2 are compiler-generated temporary names. The principal sources of optimization. In this video, we are going to see about the principal source of optimization. A transformation of a program is called local if it can be performed by looking only at the statements in a basic block, otherwise it is called global. Many transformations can be performed at both the local and global levels. Local transformations are usually performed first. Function-preserving transformations. There are a number of ways in which a compiler can improve a program without changing the function it computes. The transformations. Common sub-expressions eliminations, copy propagation, dead code elimination, and constant folding. Common sub-expressions elimination. An occurrence of an expression E is called a common sub-expression if E was previously computed and the values of variables in E have not changed since the previous computation. We can avoid recomputing the expression if we can use the previously computed value. Copy propagation. Assignments of the form f is equal to g, called copy statements or copies for short. The idea behind the copy propagation transformation is to use G for F. Whenever possible after the copy statement F is equal to G. Copy propagation means use of one variable instead of another. This may not appear to be an improvement, but as we shall see, it gives us an opportunity to eliminate X. Dead code eliminations. A variable is live at a point in a program if its value can be used subsequently, otherwise it is dead at that point. While the programmer is unlikely to introduce any dead code intentionally, it may appear as a result of previous transformations. An optimization can be done by eliminating dead code. Example: I is equal to 0. If I is equal to 1, open bracket, A is equal to B plus 5, close bracket. Here, if statement is dead code because this condition will never get satisfied. Constant folding. We can eliminate both the test and printing from the object code. More generally, deducing at compile time that the value of an expression is a constant and using the constant instead is known as constant folding. Structure preserving transformations. In this video, we are going to see about structure preserving transformations. There are two types of basic block optimizations. They are structure preserving transformations, algebraic transformations. The primary structure preserving transformation on basic blocks are common sub-expression elimination, dead code elimination, interchange of two independent adjacent statements, renaming of temporary variables. Overview of loops in flow graphs. In this video, we are going to see about overview of loops in flow graphs. A graph representation of three address statements called a flow graph is useful for understanding code generation algorithms even if the graph is not explicitly constructed by a code generation algorithm. Nodes in the flow graph represent computations and the edges represent the flow of control. Natural loop. One application of dominator information is in determining the loops of a flow graph suitable for improvement. Inner loop. If we use the natural loops as the loops, then we have the useful property that unless two loops have the same header, they are either disjointed or one is entirely contained in the other. Pre-headers. Several transformations require us to move statements before the header. Therefore, begin treatment of a loop L by creating a new block called the pre-header. Computing data flow equations. In this video, we are going to see about computing data flow equations. We can perform data flow analysis by computing data flow equations using either available expression, reaching definition, or using live variable analysis. The analysis made by available expression or reaching definition is called forward analysis, and the analysis made by using live variable analysis is called backward analysis. The basic operations that are used in this kind of analysis are logical and or intersection. Logical or union. Difference. Logical and or intersection. The intersection operation is implemented as logical and. The truth table is given for the ease of computation. Logical or union. The union operation is implemented as logical or. The truth table is given for the ease of computation. Difference. The difference operations A minus B can be interpreted as first obtain negation B, then AND A with negation B. The truth table can be code improving transformations. In this video, we are going to see about code improving transformations. Code improving transformations. The code improvement can be possible by using the code improving transformations. These are generally called optimization techniques. Some of the codes improving transformations are discussed here under. Constant folding. This is actually compile time evaluation. This makes possible for the computations performed during the execution time itself and thus avoids the computation during the execution time. Constant folding is nothing but replacing the runtime compilation by compile time computation. Example: A is equal to 22 by 7 pointer R. In the above example, 22 by 7 can be computed during the compilation time itself than computing in each execution. Constant propagation. Propagation means propagating an entity from one statement to another statement. This is done for constants. We can understand this by an example. Consider the following three address statements. Temp1 is equal to 4. Temp2 is equal to temp1 pointer 2. Here the variable temp1 is propagated. This can be optimized given below during the compile time itself. Temp1 is equal to 4 up to temp2 is equal to 4 pointer 2. This is actually constant propagation. Constant propagation is nothing but replacement of a variable by a constant that appears on the RHS of an assignment for that variable. This is done during the compile time. The variable should not be redefined along path of its use. Variable propagation or copy propagation. Copy propagation means the use of variable v1 in place of v2. Consider the following statements. v1 is equal to v2 up to h is equal to v1 plus f, g is equal to v2 plus f minus 6. In statement 2, v2 can be used in place of v1 by copy propagation. The transformed statements will be listed below. v1 is equal to v2 up to h is equal to v2 plus f, g is equal to v2 plus f minus 6. Dead code elimination. A variable is dead if not used subsequently, that is, it is not live. The code is useless. The dead code may appear in the program generally accidentally. This dead code can be eliminated. The above discussed transformation are said to be function preserving transformations. Data flow analysis of structured flow graphs. In this video, we are going to see about data flow analysis of structured flow graphs. Flow graphs for control flow constructs such as do-while statements, have a useful property. There is a single beginning point at which control enters and a single end point that control leaves from when execution of the statement is over. We exploit this property when we talk of the definitions reaching the beginning and the end of statements with the following syntax. Expressions in this language are similar to those in the intermediate code, but the flow graphs for statements have restricted forms. We define a portion of a flow graph called a region to be a set of nodes n that includes a header, which dominates all other nodes in the region. All edges between nodes in n are in the region, except for some that enter the header. The portion of flow graph corresponding to a statement S is a region that obeys the further restriction that control can flow to just one outside block when it leaves the region. We say that the beginning points of the dummy blocks at the entry and exit of a statement's region are the beginning and end points, respectively, of the statement. The equations are inductive or syntax-directed definition of the sets in of S, out of S, gen of S, and kill of S for all statements S. Gen of S is a set of definitions generated by S, while kill of S is the set of definitions that never reach the end of S. Depth first ordering in iterative algorithms. In this video, we are going to see about depth first ordering in iterative algorithms. Two ways to use flow graph theory to speed data flow analysis. The first is an application of depth first ordering to reduce the number of passes that the iterative algorithms, and the second uses intervals or the T1 and T2 transformations to generalize the syntax-directed approach. In all the problems studied so far, such as reaching definitions, available expressions, or live variables, any event of significance at a node will be propagated to that node along an acyclic path. Similarly, if an expression x plus y is not available at the entrance to block B, then there is some acyclic path that demonstrates that fact. Either the path is from the initial node and includes no statement that kills or generates x plus y, or the path is from a block that kills x plus y and along the path there is no subsequent generation of x plus y. Finally, for a live variable, if x is live on exit from block B, then there is an acyclic path from B to a use of x along which there are no definitions of x. The reader should check that in each of these cases, paths with cycles add nothing. If the flow graph is not reducible, the depth may depend on the depth first spanning tree chosen. If A gives B is an edge, then the depth first number of B is less than that or A only when the edge is a retreating edge. Suppose we have a path along which a definition B propagates, such as 3 gives 5, gives 19, gives 35, gives 16, gives 23, gives 45, gives 4, gives 10 gives 17. Then, the first time through the loop of lines 5 gives 19, B will propagate from out of 3 to in of 5 to out of 5 and so on up to out of 35. It will not reach in of 16 on that round, because as 16 precedes 35, we had already computed in of 16 by the time B was put in out of 35. However, the next time we run through the loop of lines 5 gives 19, when we compute in of 16, B will be included because it is in out of 35. Definition B will also propagate to out of 16 in of 23 and so on up to out of 45, where it must wait because in of 4 was already computed. On the third pass, B travels to in of 4, out of 4, in of 10 and out of 10 and in of 17. So after 3 passes, we establish that B reaches block 17. It should not be hard to extract the general principle from this example. Those edges are exactly the retreating edges, so the number of passes needed is 1 plus the depth. The depth first order is also advantageous for available expressions or any data flow problem that we solved by propagation in the forward direction. Thus, we may propagate a use of variable in block 17 backwards along the path. 3 gives 5, gives 19, gives 35, gives 16, gives 23, gives 45, gives 4, gives 10, gives 17. In one pass to in of 4, where we must wait for the next pass to in order to reach out of 45. On the second pass, it reaches in of 16, and on the third pass, it goes from out of 35 to out of 3. Structure-based data flow analysis. In this video, we are going to see about structure-based data flow analysis. With a bit more effort, we can implement data flow algorithms that visit nodes and apply data flow equations no more times than the interval depth of the flow graph, and frequently the average node will be visited even fewer times than that. Whether the extra effort results in a true time savings has not been firmly established, but a technique like this one, based on interval analysis, has been used in several compilers. Further, the ideas exposed here apply to syntax-directed data flow algorithms for all sorts of structured control statements, not just the if, then, and do, while, and these have also appeared in several compilers. We shall base our algorithms on the structure induced on flow graphs by the T1 and T2 transformations. We are concerned with the definitions that are generated and killed as control flows through a region. Unlike the regions defined by if or while statements, a general region can have multiple exits, so for each block B in region R, we shall compute sets gen R, B and kill R, B of definitions generated and killed, respectively along paths within the region from the header to the end of block B. These sets will be used to define a transfer function trans R, B of S that tells for any set S of definitions what set of definitions reach the end of block B by traveling along paths wholly with R, given that all and only the definitions in S reach the header of R. As we have seen, the definitions reaching the end of block B fall into two classes: those that are generated within R and propagated to the end of B independent of S. Those that are not generated in R but that also are not killed along some path from the header of R to the end of B, and therefore area in trans R, B of S if and only if they are in S. Thus, we may write trans in the form trans R, B of S is equal to gen R, B U of S up to kill R, B. The heart of the algorithm is a way to compute trans R, B for progressively larger regions defined by some T1, T2 decomposition of a flow graph. For the moment, we assume that the flow graph is reducible, although a simple modification allows the algorithm to work for non-reducible graphs as well. The basis is a region consisting of a single block B. Here, the transfer function of the region is the transfer function of the block itself, since a definition reaches the end of the block if and only if it is either generated by the block or is in the set S and not killed. That is, gen B dot B is equal to gen of B. Kill B dot B is equal to kill of B. Now let us consider the construction of a region R by T2, that is, R is formed when R1 consumes R2 as suggested. First, note that within region R there are no edges from R2 back to R1, since any edge from R2 to the header of R1 is not a part of R. Thus, any path totally within R goes optionally through R1 first, then optionally through R2, but cannot then return to R1. Also note that the header of R is the header of R1. We may conclude that within R, R2 does not affect the transfer function of nodes in R1, that is, gen R, B is equal to gen R1, B. Kill R, B is equal to kill R1, B. For all B in R1, the definition is generated within R2. The definition is generated within R1, reaches the end of some predecessor of the header of R2 and is not killed going from the header of R2 to R8. The definition is in the set S available at the header of R1, not killed going to some predecessor of the header of R2 and not killed going from the header of R2 to B. Thus, let G be the union of gen R1, P for an predecessors P of the header of R2, and let K be the intersection of kill R1, P for all those predecessors P. Then if S is a set of definitions that reach the header of R1, the set of definitions that reach the header of R2 along paths staying wholly within R is GU of S minus K. Therefore, the transfer function in R for those blocks B in R2 may be computed by gen R dot B is equal to gen R2 dot B U of G minus kill R2, B. Kill R, B is equal to kill R2, B U of K minus gen R2, B. The general situation, note that R consists of R1 plus some back edges to the header of R1, which is also the header of R of course. A path going through the header twice would be cyclic. The definition is generated within R1 and does not need the back edges incorporated into R in order to reach the end of B. The definition is generated somewhere within R1, reaches a predecessor of the header, follows one back edge, and is not killed going from the header to B. If we let G be the union of gen R1, P for all predecessors of the header in R, then gen R, B is equal to gen R1, B U of G minus kill R1 dot B. A definition is killed going from the header to B if and only if it is killed along all acyclic paths, so the back edges incorporated into R do not cause more definitions to be killed. That is, kill R, B is equal to kill R1, B. Algorithm: structure-based reaching definitions. Input: a reducible flow graph G and sets of definitions gen of B and kill of B for each block B of G. In of B for each block B. Method: find the T1, T2 decomposition for G. For each region R in the decomposition from the inside out, compute gen R dot B and kill R, B for each block B in R. If U is the name of the region consisting of the entire graph, then for each block B, set in of B to the union over all predecessors P of block B of gen U, P. Some speed UPS to the structure-based algorithm. First, notice that if we have a transfer function GU of S minus K, the function is not changed if we delete from K some members of G. Thus, when we apply T2, instead of using the formulas, gen R, B is equal to gen R2, B U of G minus kill R2, B. Kill R, B is equal to kill R2, B U of K minus gen R2, B. We can replace the second by kill R, B is equal to kill R2, B UK. Thus saving an operation for each block in region R2. Another useful idea is to notice that the only time we apply T1 is after we have first consumed some region R2 by R1, and there are some back edges from R2 to the header of R1. Instead of first making changes in R2 because of the T2 operation and then making changes in R1 and R2 due to the T1 operation, we can combine the two sets of changes if we do the following. Using the T2 rule, compute the new transfer function for those nodes in R2 that are predecessors of the header of R1. Using the T1 rule, compute the new transfer function for all the nodes of R1. Using the T2 rule, compute the new transfer function for all the nodes of R2. Note that feedback due to the application of T1 has reached the predecessors of R2 and is passed to all of R2 by the T2 rule. There is no need to apply the T1 rule for R2. Handling non-reducible flow graphs. In this video, we are going to see about handling non-reducible flow graphs. If the T1, T2 reduction of a flow graph stops at an limit flow graph that is not a single node, then we must perform a node splitting. Splitting a node of the limit flow graph corresponds to duplicating the entire region represented by that node. The result of the splits is that some of the nodes of the original graph will have more than one copy in the region represented by the one node graph. The only difference is that when we split a node, the gens and kills for the nodes of the original graph in the region is represented by the split node must be duplicated. For example, whatever the values of gen and kill are for the nodes in the two-node region on the left become gen and kill for each of the corresponding nodes in both two-node regions on the right. At that final step, when we compute the ins for all the nodes, those nodes of the original graph that have several representatives in the final region have their ins computed by taking the union of the ins of all their representatives. In the worst case, splitting of nodes could exponentiation the total number of nodes represented by all the regions. Thus, if we expect many flow graphs to be non-detectable, we probably should not use structure-based methods. Fortunately, non-reducible flow graphs are sufficiently rare that we can generally ignore the cost of node splitting. Symbolic Debugger. In this video, we are going to see about Symbolic Debugger. A symbolic debugger is a system that allows us to look at a program's data while that program is running. The debugger is usually called when a program error such as an overflow occurs or when certain statements indicated by the programmer in the source code are reached. Once invoked, the symbolic debugger allows a programmer to examine and possibly change any of the variables that are currently accessible to the running program. In order for a user command like show me the current value of A to be intelligible to the debugger 8, there must be a way to associate an identifier like A with the location it represents. That's the portion of the symbol table that assigns to each variable a location. Example, a place in a global data area or in an activation record for some procedure must be recorded by the compiler and preserved for the debugger to use. There must be scope information so we can disambiguate references to an identifier that is declared more than once, and so that we can tell, given we are in some procedure P, what other procedures data is accessible and how do we find that data on the stack or other runtime structure. Again, this information must be taken from the symbol table of the compiler and preserved for future use by the debugger. We must know where are the program when the debugger is invoked. This information is embedded by the compiler in the call to the debugger when the compiler handles the user-declared invocation of the debugger. It is also obtained from the exception handler when a runtime error causes the debugger to be called. In order that program location information mentioned in tree makes sense to the user, there must be a table associating each machine language statement with the source statement from which it came. This table can be prepared by the compiler as it generates code. Issues in the design of a code generator. In this video, we are going to see about issues in the design of a code generator. The following issues arise during the code generation phase: input to code generator, target program, memory management, instruction selection, evaluation order, input to code generator. The input to the code generation consists of the intermediate representation of the source program produced by front end, together with information in the symbol table to determine runtime addresses of the data objects denoted by the names in the intermediate representation. Target program. The output of the code generator is the target program. The output may be absolute machine language, relocatable machine language, assembly language, memory management. Names in the source program are mapped to addresses of data objects in runtime memory by the front end and code generator. Instruction selection. The instructions of target machine should be complete and uniform. The former statement can be translated into the later statement as shown below. Evaluation order. The order in which the computations are performed can affect the efficiency of the target code. Some computation orders require fewer registers to hold intermediate results than others. Overview of the target machine. In this video, we are going to see about overview of the target machine. Familiarity with the target machine and its instruction set is a prerequisite for designing a good code generator. The target computer is a byte addressable machine with 4 bytes to a word. It has n general purpose registers R0, R1 up to Rn-1. It has 2 address instructions of the form op source destination, where op is an opcode and source and destination are data fields. It has the following opcodes: MOV, that is move source to destination; ADD, add, that is add source to destination; SUB, sub, that is subtract source from destination. The source and destination of an instruction are specified by combining registers and memory locations with address modes. Address modes with their assembly language forms. For example, MOV R0 M stores contents of registers R0 into memory location M. MOV 4, that is R0, M stores the values contents 4 plus contents R0 into M. Introduction to Runtime Storage Management. In this video, we are going to see about Introduction to Runtime Storage Management. Information needed during an execution of a procedure is kept in a block of storage called an activation record, which includes storage for names local to the procedure. The 2 standard storage allocation strategies are static allocation, stack allocation. In static allocation, the position of an activation record in memory is fixed at compile time. In stack allocation, a new activation record is pushed onto the stack for each execution of a procedure. The record is popped when the activation ends. The following three address statements are associated with the runtime allocation and deallocation of activation records: call, return, halt, and action, a placeholder for other statements. We assume that the runtime memory is divided into areas for code, static data, stack. Concept of simple code generator. In this video, we are going to see about concept of simple code generator. A code generator generates target code for a sequence of 3 address statements and effectively uses registers to store operands of the statements. For example, consider the 3 address statement A is equal to B plus C. It can have the following sequence of codes: add rj, ri, cost is equal to 1, double backslash if ri contains B and rj contains C. Or add c, ri, cost is equal to 2, double backslash if C is in a memory location. Or mov c, rj, cost is equal to 3, double backslash move C from memory to rj and add rj, ri. A code generation algorithm. The algorithm takes as input a sequence of 3 address statements constituting a basic block. For each 3 address statement of the form x is equal to y op z, perform the following actions. Invoke a function getRegister to determine the location L where the result of the computation y op z should be stored. Consult the address descriptor for y to determine y dash, the current location of y. Prefer the register of y dash if the value of y is currently both in memory and a register. If the value of y is not already in L, generate the instruction mov y dash, L to place a copy of y in L. Generate the instruction op z dash, L where z dash is the current location of z. Prefer a register to a memory location if z is in both. Update the address descriptor of x to indicate that x is in location L. If x is in L, update its descriptor and remove x from all other descriptors. If the current values of y or z have no next users, are not live on exit from the block, and are in registers, alter the register descriptor to indicate that after execution of x is equal to y op z, those registers will no longer contain y or z. Generating code for pointer assignments. The table shows the code sequences generated for the pointer assignments. A is equal to pointer P and pointer P is equal to A. Overview of register allocation and assignment. In this video, we are going to see about overview of register allocation and assignment. The use of register operands instead of memory operands is always the faster and shorter. This also means that proper use of registers help in generating the good code. There are various strategies for deciding how to use these registers and what values are to be stored in the registers. In other words, certain strategies are adopted by the compiler for register allocation and assignment. That is, as we know that register handling in code generation can be done using register allocation and assignment. The most commonly used strategy to register allocation and assignment is to assign specific values to specific registers. For instance, for base addresses, separate set of registers can be used. Similarly, for storing the stack pointers again, a separate set of registers can be assigned. Arithmetic computations can be done using separate set of registers. Remaining set of registers are used by the compiler for suitable purposes. The advantage of this approach is that the design process of compiler for code generation becomes simplified. The disadvantage of this method is that the design of compiler becomes complicated because of restrictive use of registers. At the same time, certain set of registers remain totally unused over substantial portions of code, and some set of registers get overloaded. But this disadvantage can be tolerable by most of the compiler, and this approach can be adopted in most of the computing environment. Various strategies used in register allocation and assignment, and those are global register allocation, usage count, register assignment for outer loop, graph coloring for register assignment. Overview of directed acyclic graph. In this video, we are going to see about overview of directed acyclic graph. A DAG for a basic block is a directed acyclic graph with the following labels on nodes. Leaves are labeled by unique identifiers, either variable names or constants. Interior nodes are labeled by an operator symbol. Nodes are also optionally given a sequence of identifiers for labels to store the computed values. Dags are useful data structures for implementing transformations on basic blocks. It gives a picture of how the value computed by a statement is used in the subsequent statements. It provides a good way of determining common sub-expressions. Input a basic block, output a DAG for the basic block containing the following information. A label for each node. For leaves, the label is an identifier. For interior nodes, an operator symbol. For each node, a list of attached identifiers to hold the computed values. X is equal to y op z, x is equal to opy, x is equal to y. Method. Step 1. If y is undefined, then create node of y. If z is undefined, create node of z for case of I. Step 2. For case of 1, create a node of OP whose left child is node of Z. Checking for common sub-expression, let n be this node. For case of 2, determine whether there is node of OP with one child node of Y. If not, create such a node. For case of 3, node n will be node of Y. Step 3. Delete x from the list of identifiers for node of x. Append x to the list of attached identifiers for the node n found in step 2 and set node of x to n. Example, consider the block of 3 address statements. T1 is equal to 4-pointer I, T2 is equal to A of T1, T3 is equal to 4-pointer I, T4 is equal to B of T3, T5 is equal to T2 pointer of T4, T6 is equal to prod plus T5, prod is equal to T6, T7 is equal to I plus 1, I is equal to T7. If I lesser than or equal to 20, go to 1. Concept of p-hole optimization. In this video, we are going to see about concept of p-hole optimization. A statement-by-statement code generation strategy often produces target code that contains redundant instructions and suboptimal constructs. The quality of such target code can be improved by applying optimizing transformations to the target program. A simple but effective technique for improving the target code is p-hole optimization, a method for trying to improving the performance of the target program by examining a short sequence of target instructions called the p-hole and replacing these instructions by a shorter or faster sequence whenever possible. The p-hole is a small, moving window on the target program. The code in the p-hole need not contiguous, although some implementations do require this. It is characteristics of p-hole optimization that each improvement may spawn opportunities for additional improvements. We shall give the following examples of program transformations that are characteristic of p-hole optimizations. Redundant instructions elimination, flow of control optimizations, algebraic simplifications, use of machine idioms, unreachable code. Generating code from Dags. In this video, we are going to see about generating code from Dags. The advantage of generating code for a basic block from its DAG representation is that from a DAG, we can easily see how to rearrange the order of the final computation sequence. Then we can start from a linear sequence of 3 address statements or quadruples. Rearranging the order. For example, consider the following basic block. T1 is equal to A plus B, T2 is equal to C plus D, T3 is equal to E minus T2, T4 is equal to T1 minus T3. Generated code sequence for basic block. MOV A, R0, add B, R0, MOV C, R1, add D, R1, MOV R0, T1, MOV E, R0, sub R1, R0, MOV T1, R1, sub R0, R1, MOV R1, T4. Rearranged basic block. Now T1 occurs immediately before T4. T2 is equal to C plus D. T3 is equal to E minus T2. T1 is equal to A plus B. T4 is equal to T1 minus T3. Revised code sequence. MOV C, R0, add D, R0, MOV A, R0, sub R0, R1, MOV A, R0, add b comma r0, sub r1 comma r0, mov r0 comma t4. In this order, two instructions mov r0 comma t1 and mov t1 comma r1 have been saved. Dynamic Programming Code Generation Algorithm. In this video, we are going to see about Dynamic Programming Code Generation Algorithm. Some recursive algorithms are very inefficient because they solve the same sub-problem several times. For example, is the case with the Fibonacci function. A rather obvious solution is to store the results in a table as they are computed, and then check the table before solving a sub-problem to make sure that its value hasn't already been computed. This is known as memoization. Even more efficient is to try to find a linear that has topological order in which the sub-problems can be solved, and then solve them in that order, knowing that we need the result of a specific sub-problem. It has already been computed. This is dynamic programming. Recursive function. Function fib of n. If n lesser than or equal to 1, then return 1. Else return fib of n minus 1 plus fib of n minus 2. Memoization Fibonacci. For I is equal to 1 to n, to a of I is equal to minus 1. Function fib of n. If a of n is equal to minus 1, then if n lesser than or equal to 1, then a of n is equal to 1. Else a of n is equal to fib of n minus 1 plus fib of n minus 2. Return a of n. Dynamic programming algorithm. There is a linear time dynamic programming minimum G bottom-up algorithm for computing the cost S. Compute C of I at node n. Consider each instruction Rk is equal to E matches the subtree and choose the minimum C of I, where C of I, the sum of C of I of n's left subtree, C of I minus 1 of n's right subtree, the cost of the instruction at n, Ri is equal to Ri of Rj, Ri is equal to Mj, Mi is equal to Rj, Ri is equal to Ri of Mj, Ri is equal to Rj. Code generator generators. In this video, we are going to see about code generator generators. Code generator generators. CGGs remove the burden of deciding what code to generate for each construct. Implementer produces a formal description of what each target machine instruction does. CG automatically searches machine description to find the instructions S that produce desired computation. Code almost as good as conventional compiler, but generation speed much slower. Berg code generator based on burst technology and was written by Christopher Fraser, Robert Henry, and Todd Probsting, and is available by anonymous FTP from kc.cs.wisc.edu. It is provided as a compressed share archive located in file pub/berg.share.z, provides an overview of the system and how to use it. iBerg, another code generator based on burst technology, but that does dynamic programming at compile time, was written by Fraser, Hansen, and Probsting and is available by anonymous FTP from ftp.cs.princeton.edu. It is provided as a compressed tar archive located in file pub/iberg.tar.z or pub/iberg.tar.zip, that is FRAH92, provides an overview of the system and how to use it.